All right, good morning, ladies and gentlemen. My name is John Olson, and on behalf of NASA and Exploration Systems, I'd like to welcome you to our Exploration NEO Objectives Workshop, or ExploreNOW. I think we have a very action-packed and full day for you, not only today, but as well as tonight's reception and then tomorrow. With that, I'd like to do some brief logistics and administrative comments first. For today's meeting, in terms of emergency exits, we can just go right out the door, and the primary door to the hotel is the best route. Looking at bathrooms, those are just down the hall past the bank of elevators and to the right. And likewise, there's a business center directly across the hall. They do accept credit cards there. And for those of you who are on wireless today, the name of the wireless for this room is the Mayflower Meeting. And on the back of your name tag, conveniently, is your username and password. So if you need to connect wirelessly, that should work out well for you. If you need any assistance, we have plenty of audio-visual people here to help you out. Likewise, for charging of laptops or anything of that sort, if you don't have a power cord at your table, not all tables do, we also have convenient charging stations in the back on those two left pillars. So you may charge up the battery a little bit later there if you so desire. Additionally, in addition to the wireless that will be on for the two-day period, we are also web streaming this entire event live as we go through the course of activities. We also have an AnyBot robot here as well. So I encourage you to keep that in mind, that we are live and going out streaming to the public. So keep it family show. Now we also have a very aggressive but highly action-packed agenda for you today. So my primary job is going to be keeping us on time and consistent with the agenda. So I would like to call out a couple of key folks who have been vital to making this very exciting base planning event for NEOs such a success. And through the leadership and diligent planning, I'd like to first mention Marguerite Broadwell. She has been the primary focal point for this. She has absolutely done a phenomenal job, and so I would like to specifically mention her outstanding efforts, as well as those of Erin Mahoney, who raised a hand. I don't see Erin. She's probably up there. She's in the back. Erin has also done a phenomenal job. Sasha Sims and Phil Mongan. The four of them have been phenomenal. So I'd like to say thank you. It's also Marguerite Broadwell's birthday yesterday. So happy birthday. So to open up today's Explore Now session, I'd like to invite up to the front for opening remarks the Associate Administrator for Exploration Systems Mission Directorate here at NASA headquarters, Doug Cooke, an icon in the exploration arena.
Good morning. I want to welcome you as well to this Exploration of NEO's Objectives Workshop. I want to thank you for taking time out of your busy schedules to be here and contribute to this. It is a working meeting. We plan to put you to work. I did note this morning that I know most of you, and for those who I don't know, I would like to meet you while you're here. I also want to thank those who are participating through the live web stream. We will be getting inputs through that mode as well. We were limited in the size of this, so we wanted to make sure that we open it up as widely as possible. On April 15th of this year, President Obama made a speech at Kennedy Space Center and challenged NASA to fly a human mission to a NEO by the mid-2020s, by 2025. At that point, we started in earnest planning for that. I actually began thinking about this particular workshop and planning for it and finding the time when it would work best. But we thought this is an important part of the process for us in understanding what we need to know about near-Earth objects and how to plan for human missions and what the objectives should be. And that's most important. What you see in the media and conversations everywhere is more or less talking about how we get there, the rockets, the crew vehicles, and that sort of thing. What's very important and probably most important in terms of what we give back to the public is what we learn when we do these missions and what we bring back. So this is an important opportunity for us to become collectively better informed and to learn from your varying perspectives on near-Earth objects and what we can learn from them. We held a similar workshop on lunar exploration in 2006 and actually have structured this one based initially at least on what we did there. We thought that was very successful, very productive, and actually has guided our mission studies and architecture work and planning on how we would explore the moon. It actually, through an evolution of understanding the objectives for lunar science and lunar exploration objectives and all the other objectives that fell into about 6 themes, as those evolved in our discussions with the community, with our international partners, it actually evolved. The planning changed in midstream because we found we were missing some of the objectives that were important. And so in that work, the activity that started with the kind of thing that we're going to do here actually influenced us in a major way in terms of laying out the priorities for lunar missions. So we have high expectations of what we will learn here and what we will produce in terms of objectives for near-Earth object missions, and we look forward to that. The primary goals of the workshop are to increase our collective understanding of near-Earth objects, to convey the status of what we understand about them now, mission results from missions that have gone to near-Earth objects, and to capture your ideas and your idea of objectives for these types of missions. We have invited experts from academia, international partners, industry, other federal agencies, and so we are looking to this broader community than just our normal NASA folks who also contribute obviously very much to this, but open it up to the broader community in order to make sure that we capture as much information and understanding as possible. Specifically, we'll focus on what we can learn, what we do when we explore, once we arrive at a near-Earth object. There are other forums and activities where we talk about how we get there, once again, the vehicles and that sort of thing. What's most important from this activity is to understand what we'll learn. What is it that we should do in exploring near-Earth objects? So we'll start off with a series of briefings that will convey what is known about NEOs from experts, as well as mission results from the various missions that have brought back information from near-Earth objects. We do have international partners with us, as I mentioned. We have representatives from Japan, European, Canadian, German, and Korean space agencies. So this is an opportunity for us to get a more of a worldview of what we can expect to learn and what we should plan for in exploring near-Earth objects. As a part of the discussion, we will talk about the exploration framework that we are working with international partners at this point. For those of you who may not be aware, we have organization, a worldwide organization or group, coordination group that includes 13 other space agencies beyond NASA. So there are 14 space agencies currently participating in developing a framework for exploration. We'll have a panel session a little later with representatives from science, planetary defense, and the administration to discuss objectives that they envision for near-Earth objects. After this, after the series of information that will be presented, we'll then be collecting your ideas on objectives, and that will lead us to discussion of those in breakout sessions, where we'll elaborate on the objectives, and then toward the end of the effort tomorrow, we'll have out briefs from these working groups in order to communicate the results of all that to the broader group. So I look forward to the results from this. I think it will produce a good product that we'll work with for probably years to come, as we did from the lunar objectives workshop that we did, and it'll illuminate exciting opportunities for exploration of near-Earth objects, and we'll learn more about. In the end, we'll learn more about our own solar system and its evolution. So I hope you enjoy the workshop. I encourage you to participate enthusiastically. We do want to get your ideas. We do want to put you to work, and we want to get the benefit of your knowledge and experience in this area, so that we can collectively learn much more about this area of exploration. So once again, welcome, and I look forward to meeting more of you today and tomorrow, and I think this will be an interesting 2 days. So with this, I'll pass it back to John. Thank you.
Well, as Doug aptly said, this workshop is about engagement. It's about two-way engagement, both providing information and taking in information and baselining that as the best and brightest and most current compilation of NEO information possible. So with that, we're going to have several speakers today. I do request that we use the forward clicker. Since we are web streaming, it'll be a little bit cleaner rather than saying advanced slide to the groups. Additionally, I would like to mention that we have this morning, first up, a trio, each of which is representing a world-class level of knowledge, and we're trying to first with Tom Jones, who's an astronaut, author, and general NEO guru. He is going to be briefing on why go to a NEO. Then we'll have Lindley Johnson, who heads up our NEO office at the Science Mission Directorate here at headquarters, speaking on opportunities for NEO exploration. And then we'll have Bill Ailor talking about considerations for planetary defense. So instead of me popping up each time between those, I'll introduce those first three here. And so without further ado, I'd like to invite Tom up for his briefing on why go to a NEO.
Hey, good morning, everybody. How are you this morning? It's great to wake up with you and be here to talk about exploration of near-Earth objects. I can look out in the audience and I see people who I've learned from over the years, people I've worked with recently on this idea of sending human explorers to NEOs. I see some of my astronaut colleagues here. And of course, out here via the web, we've got many more people who I've worked with and who I'm glad to see this morning following our discussions. I'd like to talk with you about kicking off this subject in the following way. I think that near-Earth objects are a class of destinations that actually have risen to the top of our attention because of a number of factors. There are political factors, technical factors, budgetary factors, and we should take advantage of the fact that these now seem to be accessible to us as we plan our forays into deep space in the coming years. I remember as a student at the Lunar and Planetary Lab with some of my colleagues here, we used to have hallway conversations about how we could actually get people to these objects from the point of view of scientific exploration. Back in the 80s, I went to a NASA-sponsored workshop where we discussed how we could use resources from these objects to bootstrap our way into the solar system with robotic and human exploration. In the 1990s, we had the idea of the Space Exploration Initiative, where we would develop the capability to visit not only the moon, but the asteroids and then eventually Mars. And of course, that didn't come to fruition, but as I spent my time in Houston during my astronaut career, I continued to think and read about the potential for exploring near-Earth objects. And it was a real struggle back in the 90s to keep this idea current because we were focused on the space shuttle, designing and building the space station. Even the moon was out of our reach back then. And of course, over time, those conditions and circumstances have changed, and now we have the opportunity to think about deep space exploration with human explorers once again. We've got the moon in our capabilities. We've got near-Earth objects now, and these are stepping stones, I think, potentially for getting to Mars eventually. And I had the unique opportunity back in 2001 at the International Space Station doing a spacewalk to be outside working on the construction of that facility while we landed the first robot explorer on a near-Earth object when the Near-Shoemaker spacecraft ascended to the surface of 433 Eros. So I was outside thinking, it can't get any better than this, doing a spacewalk 200 miles up above the Earth, when I hear through my radio headset the fact that we've landed a probe on a near-Earth object. And I thought, yes, it can get better than this. Someday a human explorer could actually be doing a spacewalk on the surface of one of these objects. And so that rekindled, I think, my interest in this subject, and I've been pursuing it ever since. Now we're developing deep space capabilities in our future that I think will bring within our grasp the surfaces and the knowledge locked up in these near-Earth objects. So let me go to a brief overview of what I'd like to tell you about as we discuss objects ranging from the city-sized Eros to Itokawa, the object visited in 2005 by the Japanese Hayabusa probe. Just to give you a sense of scale, as an astronaut doing a spacewalk on the ISS over in the lower right corner there, you see that's the kind of windjammer of the stars that I was working on back in 2001. And when I tried to get my mind around during that spacewalk the fact that you could actually be conducting field exploration on an object like Itokawa or its larger cousins, it really brought home the challenge of exploration that lies in our future as we contemplate visiting objects like this that come close to the Earth. And here's the way I'd like to cover my discussion today. Talk about the various factors in my mind that make NEOs an attractive subject for our future exploration discussions, as well as the moon, as well as the moons of Mars, as well as eventually Mars itself. So here are the factors: accessibility of these objects and how they're close to our capabilities today, the science of our origins that we'll address by going there, human survival as a driver for sending human explorers into the inner solar system, resources for exploration and how we can use those to increase and conduct more efficient exploration, more economical exploration in the future. And finally, using the experience we gain at NEOs as stepping stones to more distant, ultimate destinations like Mars. Now, you can graph out those 5 factors that I'm going to talk about this morning in a list, or you can map them in a series of ideas that I'm working with from the Institute of Human and Machine Cognition right now for NASA headquarters and the ESMD folks. But you see across the top tier of ideas here, we've got science, resources, exploration of other solar system destinations that are enabled by near-Earth object exploration, cutting-edge technical capabilities that come our way, the accessibility factors that I'll talk about in a moment, and finally on the far right, the planetary defense motivation. And the nice thing about mapping these in terms of ideas is that a lot of these ideas are cross-cutting and complementary. They feed into each other. For example, in the second column here under valuable resources, if we can tap into the resources on near-Earth objects. That will enable us to further increase our exploration capabilities, which then leads to better exploration of other solar system destinations like Mars down the road. And in the same way, the knowledge that we get from operations around near-Earth objects at the bottom center will increase our capability to do planetary defense missions with robots, for example, in the future. So that's just another way of approaching this, and I think in our breakout sessions today we'll have a chance to look at these cross-cutting opportunities from near-Earth objects. So let's look first at accessibility. Very briefly, the lunar missions 40-plus years ago gave us access to the moon 3 days away. But it turns out that in terms of rocket power, the near-Earth objects that we can visit in the Earth-Moon vicinity over the next few decades actually are more attractive in terms of visitation by our systems than even the lunar surface. So on this plot, you can see at the center, the lunar outpost delta V required to do a lunar round trip is 9.1 kilometers per second. We already know on the lower far right portion of the graph that a number of near-Earth objects in our catalogs already can be reached for round-trip delta Vs, changes in velocity, of on the order of 7 down to even 5 kilometers per second round trip. So it really is true that near-Earth objects can be reached for less oomph, if you will, than going to a lunar outpost and back. And even the Martian moons require less delta V than reaching a lunar outpost and return. And that's because of the moon's gravity well and the lack of an atmosphere to use for aerobraking, for example. But what the important caveat in this discussion, though, is that while near-Earth objects may be more accessible in terms of rocket power, of course they take longer trip times to reach, on the order of several months for most of these objects, and the phasing of these orbits of near-Earth objects that are in Earth-like orbits, the most accessible to us, the phasing of those opportunities for launch occur only every few years. So for a given object, you might not have frequent launch opportunities, and of course your trip times are in the order of months, which challenges us in terms of human endurance and human logistics for missions like that. But nevertheless, these are the closest objects to us in terms of delta V in the inner solar system. And as an example, out of the constellation study of near-Earth object missions over the last few years, you can see a typical mission 150 days to 1999 AO10. The Earth's orbit is in green, the asteroid's in red. We launch in 2025. It takes about 5 months to do the round trip for Earth return, and you get about 2 weeks at the asteroid during this expedition to actually examine the NEO and do close-up field exploration. And the total delta V for this particular example is about 7 kilometers per second. Again, more attractive than a lunar round trip. Now, this is just one example of how a near-Earth object mission might be structured. There are many asteroids in our catalog, about 40 that are accessible to us in terms of rocket power with envisioned systems today. The important point is that we haven't discovered most of the accessible near-Earth objects that we might be able to visit with human explorers. And those discoveries will come as Earth-based and space-based search systems are upgraded in the coming decade. Let's go on to science. Now, these objects differ from the Moon and Mars in terms of their provenance. Materials from near-Earth objects are ancient materials left over from the formation of the solar system. They date back to 4.57 billion years ago in terms of some of the minerals locked up in the asteroids that we know of from meteorite samples. And they actually benchmark the origins of the solar system. These are the raw materials of the planets. And we glimpse those raw materials in our meteorite collections. Here are a number of beautiful shots of the meteorites that we might be visiting tonight at the Smithsonian, ranging from carbonaceous chondrites like Tagish Lake, water-rich, very fragile objects which represent only a small fraction of the meteorites that we recover on Earth. Murchison, another water-rich carbonaceous chondrite, ordinary chondrite, Gubara in the center, that's the most common type of meteorite that falls on us today. All of these materials, including nickel-iron objects in the upper right, silicate iron, nickel in the lower right corner, represent the kinds of materials that we might tap and bring back as samples from these near-Earth objects. And we'll gain access to the very origins of volatiles that went into making the Earth's oceans, the biological precursors, perhaps the amino acids, organic materials that jump-started biology on the ancient Earth. These are the kinds of materials that we can tap into with field exploration on NEOs. Moving on, those same kinds of raw materials of the planets that we find so valuable scientifically are those same materials that will jumpstart us in terms of getting out into the solar system and creating an economic base and an exploration resource for future decades in the 21st century. If we think of asteroids like Matilda out in the main belt visited by Near Shoemaker, it's about 50 kilometers across. It's a C-type asteroid, the most plentiful type of asteroid in the main asteroid belt. Dark, thought to be very primitive and unaltered from the earliest days of the solar system. Maybe a meteorite like Murchison is a representative of the kinds of materials we'd find there. Murchison is 12% water by weight. And of course, water is gold in space, both for rocket propellant, for breathing oxygen, and for the basis of so many industrial processes. If we can actually find in the near-Earth population extinct or dormant comets, like Tempel 1 visited in 2005 by Deep Impact, if we find objects that are even more water-rich, like dormant comets, that would be a bonanza for our resource exploitation of the inner solar system. And of course, these resources come without the moon's gravity well. So in some ways, they're more accessible, despite their distance and trip times, than resources that we might find on the moon. In going to these near-Earth objects and exploiting them for their scientific value and their resources, we are going to, along the way, require robotic precursor missions to take place, and then human expeditions will demand of us the very finest experiences from our Apollo heritage, our shuttle space station experience, and leverage those into a deep space capability. We're going to have to change the way we think about visiting these objects in terms of the way we operate. So close to home now, where we have almost constant communication and almost no delay in talking to our crews on the space station. If we go out to a NEO, we're going to be dealing with tens of seconds of light time delay. We're going to require increased autonomy of our spaceships, and all of those factors will increase our ability to reach further destinations like the Moon and Mars one day. So think of NEOs as rehearsal for more distant and more ambitious destinations to come. Apollo 8 and Apollo 10 back in the late 60s paved the way as test flights for the first lunar landing. So NEO missions offer us a way to test our hardware, close to home, if you will, just a few million miles from Earth rather than going all the way across the Gulf to Mars. We'll get the deep space experience after a few NEO missions to then leave those destinations and turn to more difficult exploration challenges. And the nice thing about NEOs, in that they're so small and have no inherent gravity to speak of, is that we don't need a complicated and expensive lander to do this exploration. So we can move our way into deep space in smaller steps without having to take the big development leaps required, for example, establishing a big presence on the moon, although NEOs lead naturally to going to the moon next after initial forays out there. And a glimpse of the Earth-Moon system from Near Shoemaker gives you an idea of what human explorers might see as they take the first tentative steps into the inner solar system with NEOs as their destination. We shouldn't minimize the exploration challenges of going to these objects. Even Itokawa, which is only half a kilometer across, is an object that's got the surface area of Vatican City. So a few astronauts tackling Vatican City as field geologists could actually have quite a field day for several weeks. These are not minimal exploration challenges. So rolled up into the surface area of these objects, you're really going to find some surprises. Every time our spacecraft have visited NEOs, we've been surprised, and we will when we get there with human explorers. And we're going to hear from Bill Ailor in a moment about the value of NEO exploration in terms of planetary defense, but it seems to me there's no more fundamental benefit to come from human exploration in the coming decades than acquiring the knowledge required to prevent a cosmic catastrophe from occurring on the Earth. We'll get there with robots eventually. Over the course of a half a century of robotic exploration, we might acquire the knowledge needed to prevent future impacts. But if we send human explorers for a variety of reasons, they will rapidly acquire during their experience on a number of NEOs the civil engineering knowledge needed to prevent a future catastrophe. And what I think more fundamental way to identify human spaceflight as valuable than to take this message to the public, that we're stopping a natural catastrophe from occurring for the first time in Earth's 4.5 billion year history. Now think about the human appeal, the participatory exploration opportunities for NEO exploration. Astronauts look back from Earth on Apollo, back from the moon on Apollo at the Earth, and of course you know the story about covering up the Earth with your thumb from the lunar surface. Well, when astronauts voyage to near-Earth objects, they're going to be a few million miles away. And if you can see it here in the glare of the lights, when you're at about 0.05 of an AU, a few million miles from Earth, the Earth will look like a BB about halfway down the length of this table to your apparent vision. And so that kind of distance put between us and our familiar Earth-Moon system, I think, will really change the way we think about ourselves as a species, as explorers. Imagine people looking back at their home from that distance, and then imagine them on the surface of a weird alien world for the first time where there's almost no gravity, you're in near free fall, and yet you're trying to do field geology in a very detailed way with new systems, new capabilities, and of course inventing techniques when you get there to succeed in your mission. And I think that will be a really incredible experience for the human species and a new horizon that we'll unwrap by visiting NEOs with human explorers. So next steps in our exploration of NEOs, I think fundamentally we have to start with completing the rapid search for near-Earth objects across the inner solar system. We can do this job with ground-based systems. The National Research Council has outlined some of the techniques that are available for us for doing that. It'll take several decades for those search techniques from the ground to bear fruit and give us a fairly complete understanding of the near-Earth population for both hazard prevention and for identifying exploration targets. If we do it from space, with some small, modest telescope systems that can follow Venus around in an interior orbit to that of the Earth's, we can actually map or catalog most of the near-Earth population, both in terms of hazards and exploration opportunities, within a few years. So for the cost of a single, for example, robotic Mars exploration mission, we can unlock this NEO catalog. And in the course of perhaps 3 years, for example, once a telescope like that is operational, we could discover about 500 objects that are greater than 30 meters in diameter that are accessible to human explorers. And for those objects greater than 60 meters across, about 100 of those. And that's for a delta V criterion that's actually rather strict, 5.5 kilometers of delta V, kilometers per second of delta V. So you can imagine the target set being greatly expanded by early investment in search systems, both on Earth and in space. And then we can do a number of research and development steps that will be invaluable. Of course, we need radiation countermeasures for the human explorers on these multi-month missions beyond the magnetosphere. We'll have to investigate new means of providing life support, reliable life support for those multi-month missions when failure means death. And finally, NEO mobility systems to get around on the surface of a near weightless asteroid gravity field. Those mobility systems can be extrapolated from the ones we use on the space station today, or we might brainstorm our way to more efficient ways of carrying crew members, perhaps in a little space pod, a little space taxi down to the surface of a NEO. All of those systems can be checked out, developed, and tested on the space station in the coming decade. There's no need to test these for the first time at a NEO. We can actually have a lot of confidence before we go to NEOs by using the facilities of the ISS. And while we're testing these systems, we need to also develop new concepts for operations, providing the crew and the spacecraft with greater autonomy far from mission control, and new ways of thinking about risk and how we accept risk for human explorers, not only on the moon, for example, but months away from a possible abort back to Earth. And finally, to enable all of this, we're going to have some capability to put together a larger spacecraft than we've been talking about in low Earth orbit, so we can, or high Earth orbits for that matter, Lagrange points for departing for near-Earth objects. So let me wrap up. I think that NEOs, there are next steps to NEOs, but NEOs should be our next step in human space exploration. We've got the moon nearby that we can turn to at any time. The vehicles that we develop for near-Earth object exploration give us that capability as well. And there are a number of compelling attractions that should excite us and our international partners in exploration. Near-Earth objects, of course, are accessible with the systems that we envision for the coming 10 or 20 years. We've got this science opportunity of returning ancient samples of the solar system's origins. They're interdisciplinary fields of science that will benefit from sample return and field exploration in situ. And we open up, different from the moon and different from Mars, a third planetary surface, if you will, of materials that we can access to explore the origins of our solar system and our origins of life on this planet. We get the know-how out of our voyages there rapidly for developing the knowledge for impact prevention. We get the resources in terms of water, metals, and even some rare elements that might catalyze industry in Earth-Moon space. We bring the resources back from the asteroid locale to Earth-Moon space to develop a thriving economy off-planet. And the experience that we gain in doing all of these things will provide us with the knowledge and the hardware to be springboarding off to the moon, to Mars, and beyond. And along the way, we'll be doing things in smaller steps, robotic precursors, human expeditions to a few NEOs, then taking our sights even farther, a sustainable program with visible steps occurring along the way into deep space. And we find that, I think, NEO missions challenge our experience as explorers, but also our experience on Apollo, Space Shuttle, Space Station, working together. We actually, I think, have already the astronaut skills, and then the human experience and adaptability needed to make asteroid exploration a success in the coming decade. I'd like to thank you for your attention, and we're looking forward to all the rest of the elements of NEO exploration as we come. It's time to turn this hazard into an opportunity, and the next person to talk to you will be Lindley Johnson. Thank you.
Well, good morning. Quite a crowd we got here today. I see people from across my experience in the space business for the last 30 years or so. They wanted me to come talk to you today about opportunities on NEOs, and if I can figure out how to make this thing work, we'll be doing fine. Okay. Which is the advance? Is it this one?
Yes.
Okay. There we go. Usually on this slide, I spend time telling people about the danger of these objects, how close they come to Earth, what a disaster it would be if one of them were to hit us. You know, the sky is going to fall, it's going to rain, rocks down, a disaster. Well, unfortunately for you guys, you're calling my bluff. They don't come all that close all that often. The definition of an NEO is actually not based on the Earth at all. It's based on how close they come to the Sun in their orbits. And just because we call it an NEO doesn't mean it's always near Earth or even frequently near Earth. But those are the objects that come within about 45 million kilometers of Earth's orbit, but it could be the other side of Earth's orbit rather than where the Earth happens to be at the time. NearEarth objects could be either asteroids or comets. I don't think we're so interested in comets in this setting. But we do know of about 85 comets that come relatively close to Earth. From the Planetary Defence standpoint, we're really interested in a rather small subset of these objects, which we call potentially hazardous objects. And those are ones whose orbits come within about 5 million miles of Earth's orbit, or about 20 times the distance to the moon. Those are ones that, over the course of the centuries, indeed do pose an impact hazard to the Earth. About 20% of the NEOs that we have discovered do come within this zone of Earth's orbit. But by definition, all of the objects that are going to be human accessible, at least in the near term, are by definition potentially hazardous objects because they need to come at least that close for us to be able to get to them. Let me talk about what NASA has been doing over the last few years to try to find all these objects. Our program started in about 1998. It's a really small program, relatively speaking. On the average, we've only spent about $4 million a year of planetary ARN research and analysis funding to do this job. But the goal was to find 90% of NEOs larger than 1 kilometer in size within a 10-year period, which we are beyond now. We've come close to doing that, but not quite there yet. But the goal was for the 1 kilometer objects, the very large ones, which of course could represent complete disaster if they were to impact the Earth. That's why we're really interested in those to begin with. But we've been challenged with finding those even smaller, down to the 140 meters, 100 meter class, within a 15-year period. However, we haven't been giving any additional funding to do that yet, so we're still using the same systems that we were using for the larger objects at this point in time. Speaking of those systems, this is what our program looks like right now. We have about 3 ground-based teams that are actively searching. The Linear project, MIT Lincoln Labs, has been in business for a good 12 years now, and was the backbone of finding things in the early part of the decade. Catalina Sky Survey is now our most prolific search team, finding a lot of the smaller objects from the 1 kilometer. We've really pretty well found those that are a kilometer and larger. We're probably over that 90% goal or very close to it. So they're picking up a lot of the smaller objects as they come closer to Earth. Pan-STARRS, which is an Air Force research project, has a lot of potential for finding these objects. It's not quite into operations yet. It's getting close. But the excitement here in the last year has been the use of the Wide Field Infrared Survey Explorer, which was prime mission was to do an infrared background map of the sky, very detailed. But we quickly realized a few years ago, talking with the scientists on that team, that it would make a very good asteroid detector if we were to save all the images and compare them one to the other. So it's been operating for the last 6 months, 7 months now, and done a good job of finding a lot of objects for us. In fact, Amy Manger, the PI, is over here searching for asteroids as we speak. And what are we up to now, Amy?
400 observed and discovered about 109.
Right, and you just found another comet too, I understand. So unfortunately, that's a short-lived mission, and it is has seen the beginning of the end now, with having started to see their cryostat be depleted. So it'll only be in operation for another 2 or 3 months. We'll see how it goes. But it's been a really good finder for us in that short period of time. So this is our current discovery chart. The red ones are the large 1 kilometer ones. That was our original objective. Those smaller than that is this big blue curve that goes up exponentially and probably will continue for a while. What's really becoming the driving factor, though, now with those limited capability search systems that we're using right now, just 1 kilometer or 1 meter ground telescopes, the limiting factor is going to be waiting for these objects to come within the range of those capabilities. So we're going to start to see this curve taper off and be driven more by being able to revisit the population. The total population of these objects, we believe, if you go to the 100 meter range, is in the 20s of thousands of these objects as far as NEOs are concerned. Now, of course, not all of those will be PHOs, but if you take the representative sample that we have so far, about 20% will be PHOs. There's going to be 5,000 or so objects that will be of interest to us out of this population of 20,000. This red curve represents what we have found so far, and of course we are almost complete in the large objects down here. This is as of a couple of years ago, but we have a ways to go here, and this is an exponential log scale here. So, this area here is actually a lot larger than this area down here. We need to get down to 23rd, 24th magnitude on a regular basis to find the 100 meter or so objects, which are going to be the most likely candidates for our initial human exploration missions. Oops, click too many. So bin-wise, looking at these sizes, this is where we're at, as I said, above 1 kilometer. We're 90% or better here this year. In the hundreds of meter size objects, we're doing pretty well, up to probably about 40% of the population. However, these are fewer in number, and the opportunities that they come close enough to Earth for our initial forays are very rare and limited. Most likely, we want to find objects that are in this bin, the 100 to 300 meter bin, as viable candidates for human missions. There'll certainly be a lot more of those objects, but our capabilities right now, we've only found about 8% of those, and if we drop down below 100 meters in size, our population catalog that we know right now is quite limited. Talk about a little bit more about the missions. Here's a great chart that just recently was put out with the flyby of Letitia, which is this big Hummer right here, and all the other objects, be they NEOs or not. Not all of these are NEOs certainly that have been visited so far in relative size. Eros is here from the NEAR mission. The comets that we visited are down over here. They're quite the ones that we visited are quite small. Temple 1 over here with deep impact. With Hayabusa and Itokawa, if we blow up this pixel right here, there we go. This is Itokawa, and this is pretty much the same diagram that Tom showed you with the space station visiting Itokawa. Relative scale of things, but this still is a half kilometer size object, and again, they do not visit Earth's vicinity very often, so we're going to be trying to find objects that are maybe a fifth this size as viable targets. But one of the things we've got to understand as we look at the target set is what are the right mission constraints, and we've worked with folks to do some preliminary studies on this, but we really got to understand what are the parameters that define a good target. This is the set of parameters that we've used in some preliminary studies to try to figure out what our target base is. Missions less than 180 days. Within 7.5 delta V, need to limit our return velocity. Probably want to visit something that's bigger than the capsule you're in. So we used about half the size of a football field as a cutoff here. Of course, if you are willing to accept a smaller object, there'll be more of them. If you're able to go longer, there'll be more of them. And we need to be careful about what we nestle up to as well. So looking at what we know so far in that catalog of about 7,000 objects, if we assume this kind of heavy lift capability, we know about 44 altogether that would be accessible, but more than half of those are less than 50 meters in size. 15 are accessible in the next in the 25-year time slot that we looked at for these missions. But only 3 of them would have missions that are less than 180 days. The other thing is we know very little about these objects right now, other than they're there. We haven't done any characterization on these objects. They weren't close enough, long enough for us to get good information on spin state composition and any companions. So here's the list that we know of viable candidates if you use those kind of mission constraints. The other thing about these is they don't come back around very often. Discovered in say 99, but the next time to really get a good orbit on this object is not until after we would launch a mission, if we were to use that as a candidate target. It was just not good observing opportunities from the ground. The counterintuitive thing about these objects is those that are in Earth-like orbits are sometimes the most difficult to observe because of phasing of the orbit. If it's exactly in a one-year orbit, but it's on the other side of the sun, you're never going to see it. Nemesis, I think they called it. But the closer its orbit is to Earth-like, when it goes out of phase with the Earth, the time interval between observations can become quite long, in the order of a decade or two. So those objects that are most viable for human missions from the Earth, observing from the Earth, it could be long periods of time before we can observe them. So if we find them now, we're not going to have a chance to get good observations on them from the Earth until about the time we want to launch a mission. So how do we get around that? Well, we do something different. We go to space, and an object is much more accessible from a space-based telescope, particularly one that is interior to Earth's orbit or in a Venus-like orbit. As I said, we want to find those that are in this population here, and the way to do that, we believe, based upon modeling that's been done by one of the folks that's in the room, Bill Bodke, if we have delta V's of 3 kilometers or so, there ought to be 170 objects that will be viable candidates. If we're able to up that sum, it can go into the 700 to 1,000 of these objects. And how we find them is going to an orbit interior to Earth. And the reason that works is from the Earth, you have to look at these objects away from the sun because the diurnal effects you can't observe during the daytime, certainly. So the population of these objects that are around Earth's orbit that can be seen from Earth is something like that patch of sky. But if you go interior to Earth, you're able to get a much wider swath of those objects. Plus the other thing, you're going around the sun more frequently than you are the Earth. So you revisit the entire population more frequently than you do from the Earth. We think, based on our studies, that an IR telescope on the order of half a meter or so will do the job, and we have quite a bit of experience building spacecraft of that class. So we believe we've got a pretty good handle on what that takes, both technology-wise and funding-wise. Although such a system would take a decade or so to find the entire population of NEOs up to the 100-meter class or so, as far as those that are of interest to a human mission, objects greater than 60 meters in size, let's say, about 80% of them could be found in 2 years of operation. Take about a year to get to the Venus-like orbit, and then after 2 years of operation, you would find virtually everything that you need to. So that's pretty much my bottom line. And as Tom said, the first thing to do is to complete this survey. 400, 500 potential objects, depending on what you're thinking about, within 2 years. And then, of course, for planetary defense, it adds a lot to our capability. Thank you.
Okay, well, let's talk a little bit about the planetary defense side of the house. And since there hasn't been much discussion of what the real probabilities are here, I thought I might just open with a little bit about that. We all know about the extinction events that we've talked about, and Lindley's mentioned that one of the goals of the current observation program is to discover those that might cause those kinds of events. And those are, we're very fortunate that we haven't discovered anything that looks like it's a threat in the near term. We know about 90% of those. Another more recent event is one you may be aware of. Back in 1908, a 30-meter object is estimated now came into the atmosphere and blew up over Siberia, leveled about 500 square miles of forest at that time. That was an area larger than Washington, D.C., and also New York. And so these smaller objects, which we currently can't see, are a problem for us. And I was just looking at the NASA NearEarth Object web page to see what's recent in the discovery world. And there's a 130-meter object that has now a 1 in 3,000 probability of impact in 2048. Now, generally what happens is additional measurements will lower that probability, but we all know that one of these days we'll find one where that isn't the case. And so it's really useful to be thinking about what are we going to do if we actually do find something like that, and how can we use a human mission to improve our ability to actually deflect something like that. And I might mention, by the way, the probability of a Tunguska-sized event this century is about 1 in 10. So those of you who are early in your careers might have, shall we say, the opportunity to actually do a serious mission design for this type of an event. Okay. So one of the things we want to talk about from here is what are the requirements and the objectives for doing a planetary defense mission. And you can see them here. Basically, you want to detect and verify that whatever you're seeing is actually a threat as far away from Earth as you can, and I mean far away in time. If you can see something that's going to be and get good measurements on something that's where you actually have it in range for a good period of time, that's a bonus. And also, you want to be able to move a near-Earth object to an orbit where it is no longer a hazard. So we need to have some techniques for doing that. So from the standpoint of requirements, we need to be able to perform a comprehensive survey and a search for these things and put them in a catalog and have good orbits for them, and we're working on that down to a certain size, like a kilometer at least. Probably need to go much smaller than that. We need to have precise tracking and orbit predictions to assure the threat is real as far ahead of time as you can. And this is an important factor as well, because one of the problems with doing planetary defense is for example, I mentioned that one case where we have a 1 in 3,000 chance of an impact. Sometimes it will take us years to actually develop a good understanding of what that orbit is and to really assess what the actual probability is going to be. So anything that we can do to improve our chances of making predictions like that is good. And one of the things that we worry about in the planetary defense world is false alarms. For example, that 1 in 3,000 case might be one of those. If that's the case, though, it's clear that if you're designing a mission for doing planetary defense, it's going to take you a while to design the mission. You'll have to work with the international community. You'll have to build and launch your systems. These things can take years to do. And so that whole period of time, this object's getting closer. And the closer an object like that gets, the more energy it requires to move, which means you need to move to more energetic approaches and so forth. So the problem gets a lot harder the closer an object gets in. And then lastly, you need you also need a means to apply a force to make sure that you actually can reduce the probability below where you want it to be. And that means we have to have some techniques that we have some confidence in that will actually do the job. And that also represents an area of uncertainty relative to near-Earth objects. And we'll talk about that. And then lastly, and maybe one of the most important things, is you need to be able to verify that you've actually done the job, that when you've operated on a near-Earth object for a period of time, or you've sent your kinetic impactors, that you've actually changed the orbit and it's now directed away from Earth. That'll be a very important piece. Okay, well, I'm going to have trouble reading this one from here, but basically, from the risk reduction perspective, you need to know as much as possible about the nature of the near-Earth object and how it might respond to a mitigation attempt. And as has been discussed, near-Earth objects can be made up of, say, one large body. They can be two bodies loosely held together. You can have a collection or a rubble pile. Each of these may respond a little bit differently to whatever technique you use to try to move it. And we can help understand how these properties will affect our mission success by actually doing a human mission to take a look at some of these and begin to build a database on how these objects, how it is to operate nearby these objects. The human mission, of course, expands our experiment options and increases our overall mission success from the planetary defense perspective. Humans can do multiple things and also respond to what is not known. In other words, what is not anticipated. For example, one thing that has been suggested as a way of improving our tracking capability has been to land a transponder on a near-Earth object. But suppose the near-Earth object is rotating so that the transponder is only visible a portion of the time. Or suppose that when you land the transponder, you actually kick up a little dust, and that actually will go back and cloud your reflectors or somehow affect your transponder's ability to do its job. So again, these types of insights will help us in the long term, making sure that we'll understand how we can actually improve our tracking and so forth. Oh, and then also this idea of doing multiple sensors. For example, we had a conference on this a while back, and we had some mining engineers come and talk to us about what they would do if they were given the opportunity to go and actually deal with an asteroid from their perspective. And their feeling was if they knew more about the structure and composition, that they would be able to place charges such that they could turn the near-Earth object to powder. A nice thought if you're trying to defend your planet. So, but again, these types of options require some work to gain some confidence that they would actually work. Okay, so tracking and orbit determination. As I mentioned, this is a key piece of this problem because we'll need to decide when the probability is such that we really need to go do something about an object. And one of the problems with orbit prediction is that the thermal re-radiations, very small forces, constantly act on near-Earth objects, and they change the orbit, and they make it a little bit more, a little bit less precise, and that affects our ability to estimate the probability of impact. This is particularly hard for comets. Comets, if you think about them, as they go by the sun, they outgas, and you see the tails that they generate, and that outgassing is like small thrusters operating on this body, and that will make the orbit hard to predict. And so that makes it a particularly difficult exercise. So some of the options for improving tracking are you could land a transponder or a reflector, but that requires that you may need to have something actually physically attached to a near-Earth object. So we need to understand how we would actually assure that that's going to happen. As I mentioned, dust could affect things. Information from spacecraft orbiting a station is something that would provide confidence in a couple of ways. One is that we would get information on the shape and the gravity field, but also it provides some information on anything else that we may need to worry about. For example, some of these asteroids have moons. And some of those moons are large enough themselves to be a significant hazard if they were to impact. So we would like to know that before we get there. And also for verifying success, one concept for verifying success is to basically put a spacecraft in a station-keeping mode or potentially orbiting a near-Earth object such that when you have exercised or as you are exercising your mitigation technique, that you can actually be sure that it's moving as you would like it to. And then objects for improving orbit prediction, object size, shape, rotation rate, and so forth are important, as is thermal conductivity. The loss of thermal energy by these near-Earth objects can also affect their orbits. So for moving objects, some of these, there are two basically approaches for doing that. One is called a slow push technique, where you basically would operate on an object for a long time. This is where you attach a motor and basically run a small motor for a long time, or potentially land on an asteroid and mine it and throw pieces of the asteroid off to provide some thrust. Another is to do something like the gravity tractor concept, where you'd have a spacecraft that flies very close, basically in a station-keeping mode, and the small traction between those two would slowly pull the asteroid away from its threatening orbit. These types of things would require operations in the vicinity of a near-Earth object for a long period of time. And our ability to do that is something that we would need to test. But again, information on mass, shape, and dynamics, if you're trying to use something where you've got a rocket motor on an asteroid, if that asteroid is moving or tumbling or rotating in any fashion, your time for operation of that motor is going to be limited, and so that needs to be factored into your overall design. This idea of interacting with the surface or operating in close proximity for a long period of time. The gravity tractor, clearly something like that. You'd like to have it as close to the near-Earth object as you can. You saw from some of the pictures earlier, these things have odd shapes. So trying to, if you will, station keep with a tumbling object that has a shape like that is going to be a challenge. And that would be something certainly worth looking at. And then this accurate tracking to know when it's successful is going to be a key part of any kind of slow push technique. So moving an object, some of the impulsive techniques that have been considered are basically something called kinetic impact, which a deep impact mission was something like that. That was a case where comet Tempel 1 was struck at about 10 kilometers per second by an object. And it wasn't intended to be something that would move that object, but it did a very, very small amount. So that's a concept. Another one is the detonating explosive device above, on, or below the surface of an object. And that requires certain information to do that. For example, if you exploded explosive device below the surface, you might shatter a particular type of asteroid and leave it into several large pieces. Again, if you have to go back and then start dealing with each of those pieces individually, we might have problems. In other cases, it may be a perfectly fine thing to break it into small parts. But these are the kind of things you'd like to know about. If it's a large object, you may want to try to move it without disturbing it as much as you can. NEO composition and so forth, and again, accurate tracking after the event is going to be a key, so that's something we really need to develop some capabilities. Also, I didn't mention that one of the other slow move techniques, slow push techniques, is shining a laser. This is something we hear about all the time. But one of the problems with lasers is how it will interact with the surface. And if the laser beam, for example, kicks up little clouds of dust that reduce the efficiency of the laser, that means that your laser has to dance around on the surface. And those are the kind of things, again, that you need to know. So for some of the human missions, 3 charts on this. First would be to gather and test techniques, gather data and test techniques for improving the threat prediction, mitigation, and verify the mitigation worked. And for example, testing and characterizing techniques for attaching transponders and other devices would be an important thing. In other words, we have to leave something there. How do we attach it? Test the technology required for long-term station keeping and orbiting a near-Earth object. Again, these things will have odd gravitational fields. Trying to orbit that in the long term will require fairly sophisticated controls, and gathering information on the gravitational fields on an object like that would be very helpful to us. In detailed information on the size, shape, and mass. All of these properties are useful for planetary defense reasons. And then also leaving some capability to be able to verify that we've actually done what we want is a good thing. Second chart talks about measuring the mass properties and beginning a database on the physical characteristics. And again, since we know that there is a large variety in the types of near-Earth objects, we'd like to start building a database of what this looks like. From the planetary defense perspective, the more we know, the more certain we're going to be that our techniques are going to work when we need them. I mentioned the laser impingement focus on a near-Earth object surface. The effect of human activities, for example, dust tracking reflectors, the ability to work in that environment and so forth, would be very helpful in understanding should we expect some of this stuff that we kick off to come back and immediately cause trouble to anything else that we're doing. And then lastly, just developing a model for near-Earth objects' gravitational field so that we can use that for developing the controlling techniques we'll need. And the third chart says this idea of returning samples and comparing the bulk density of these with actually what is measured on site, so that we can, again, use this as a way of combining data from robotic missions to help us understand the overall variability of near-Earth object properties. Designing spacecraft to maintain a close station with a near-Earth object, we talked about that, but one important factor is that if you're using thrusters to hold station, which is most likely what you'll be doing, you can't have the gas from those thrusters blow on the near-Earth object, because you basically counter what you were trying to do in the first place. So that is something that needs to be tested. The idea of observing with a remote spacecraft kinetic impact and measuring the effects of that would be a useful thing to do. So if we do when we do a human mission to an asteroid, it would be nice to leave something there that can observe some other things that we might want to do where you wouldn't want to have a human around. And then this idea of coordinating an in-depth human exploration with broad robotic surveys. Again, since we don't have a broad database on the variability that we can expect, this idea of using this in conjunction with robotic missions to bring all of that data together and develop a good database for how the variability would be a very useful thing from the planetary defense perspective. Thank you very much.
So with that base plane of information, we'd like to now modify the agenda just ever so slightly. Next up, we'll have Mike Hecker. He's our director for the Constellation Systems Division and Exploration Systems at NASA headquarters. And he will be talking on a broad update on our exploration study teams that have been working in earnest throughout the spring and summer. Following him will be Jay Jenkins, and Jay will talk. He is currently the study team lead for our exploration precursor robotic missions, and I think is very pleased to be having this NEO Objectives workshop. Also going to be following it up with a NEO technical interchange meeting. So I think this is prime on his hot list of information collection. So without further ado, I'll bring up Mike, and we'll proceed. Thank you.
Okay. Good morning. For the last 6 months, our mission directorate has been reviewing our existing programs and starting to develop new programs to support NASA's new strategy for exploration. And so to that end, what I'd like to do is provide you an overview of the strategy we've been using, give you a quick status on where we are with the programs, and then talk about where we need your help as we go forward. Since the new strategy came out, there has been much spirited debate about the changes that are contained in it. And there are a lot of changes in how we're going forward. But before we talk about those, I think it's important to remember what has not changed as we went forward with the strategy. This is a snapshot of the objectives that came from the Global Exploration Strategy, which several nation space agencies signed up to, including the United States, back in 2009. And these objectives, as we go forward, are still the same. We still have that, pursuing that imperative for human exploration beyond low Earth orbit, trying to gain both scientific and research knowledge as we go forward, bringing economic benefits back to the United States, and then strengthen our global partnerships. And along the way, of course, always inspiring that next generations of scientists and engineers. So this remains, as in the past, is the same objectives we're carrying forward. Something else that hasn't changed are the destinations. Our long-term ultimate goal is the human exploration of Mars. What we are doing is we're trying to open up opportunities to explore other destinations along the ways, including, as we saw, NEOs, which have a lot of interest for exploration in their own right, but also to help us as we develop our ConOps, develop our systems, and test those out as we move forward. So again, overall, the strategy is the same as far as what we're trying to achieve long-term. Now, what has changed is our near-term approach to this. What we're endeavoring to do at NASA is a balanced portfolio, a balanced set of investments in technology, with the hope that those investments then can be used to bring down the cost and actually improve the robustness of our system development, which follows. In addition, we are trying to get NASA out of the area of low Earth orbit access, and really what we'd really like to see that is turn that into a mundane day-to-day commercial activity. So we're making investments in the commercial sector to provide that service back to NASA. And of course, we want to do exploration in its own right, and therefore we're augmenting our programs with robotic precursor missions. The challenge, of course, is trying to figure out what is the right mix and where is the right balance across all of these investments as we go forward. The general strategy we're pursuing is a phased approach, again, with that long-term goal of coming up with sustainable exploration systems. To get there, starting though first with investments in technology, maturing those technologies, bringing that to bear on our system development, and at the same time doing the exploration with the robotic precursors that will help inform where we need to go next. So with that, we within the Mission Directorate have done a lot of work on formulating the programs, and I'm going to show you a snapshot that I think for those of you who joined us down at our last workshop, which was in Galveston, the end of May, you saw an earlier version of that, and I'll explain why it's changed, but it is continuing to update as we gain knowledge. And this outlines the programs and kind of flows along the strategy I just showed you for how we're trying to move forward with exploration. Up there in the top left, you're seeing the work that's being done on basic research and technology to mature some of the technical capabilities we need, followed with flight demonstrations, primarily on a set of flagship missions, but also making opportunity of our robotic missions for doing demonstrations. In addition, what you can see in there is our heavy lift capability, and then leading down eventually down into our LEO access, which right now is focused on the commercial. And I'll talk about each one of these lines just a little bit to give you the current status of what's going on. With our human research program, that is an existing program that's already underway at ESMD. As we go forward in FY11, they will continue their investments in fundamental human research with a greater emphasis on radiation effects and mitigation, which is commensurate with our look at long-term space missions. ETDD, Enabling Technologies, again, this is also a continuation of an existing program within ESMD, refocusing it, again, to support the longer-term capabilities that we're trying to show off with flagship demonstrations. This is an area, as we go forward with the workshop, that we will be looking for your help. I think Chris Moore and a couple others have a session coming up later on where we really understand that to enable NEO exploration, what are some of the technology gaps that we have today, and then based on that, what are some of the near-term demonstrations and investments we should be making. Walking down the line there, our heavy lift propulsion is focused on doing propulsion development and also looking at opportunities to partner across with commercial and other federal entities to see if there's a national capability for engines that we want to pursue. There has been a little bit of debate about whether we should bring a heavy lift vehicle into that line. That is not part of the baseline today, but that is something we're trying to assess what would be the impact, not only to what we do with heavy lift or to our propulsion technology, but to the other investments that we're making. Next on the line is the flagship missions, which is basically the flight demonstrations, mostly of what comes out of the upper lines there you see what goes on in human research, enabling technology, and heavy lift, focus on a number of areas. The one that, and Mike Conley runs this group for us, and the one that he's going to be interested from you all is the area of advanced propulsion, especially in the area of electric propulsion, and whether that makes sense to tie into some of the NEO missions that we might be looking on the robotic side. Continue down the line there to our precursor missions, broken up into two programs, one for large-size mission, one for smaller scouts. I won't go into the details of that. Jay Jenkins is going to come up in just a little bit, but as you can see from the mission profiles, a lot of emphasis on what we do around NEOs is covered there. And then moving down the line towards our actual developing LEO capabilities, we got our commercial cargo and our commercial crew. The commercial cargo, which is already underway and continues to have success with our demonstrations. The next one's coming up in September with another SpaceX launch. And then for FY11, we're trying to get efforts started away on the more dedicated towards the commercial crew activities. So that's where we are today as far as going forward with the various programs. Now, I did note that this has changed a little bit since some of you might have seen it back in Galveston if you joined us there. And that's because Well, one, there was a study done that said that large quantities of paper can actually provide you for protection, radiation protection, in the event of nuclear assault. And I understand that there is a rumor amongst industry that NASA and ESMD is doing a large number of RFIs so we can start lining our offices with that paper. I assume that's to protect us from nuclear assault from adversaries outside of Washington, D.C. That's true. That is one of our objectives, but actually we do read these things as we stand them up. And what we did is, after we had the Galveston workshop, we had a lot of input from industry, and we actually did incorporate that into our planning processes and some of the mission concepts that we're looking at. So when I showed you that previous slide and their changes, some of that was driven by the input we got from you all. We want to continue that, and this workshop here is actually the next step in that process. So as we go forward, this shows you sort of a near-term timeline of what we worked with. Back in the February-May timeframe, we did a lot of discussion within NASA and talking to ourselves on what we think is a good set of programs. We rolled that out to you all to seek input from our partners in industry and academia. We brought that on board, and actually those changes became the basis for the budget submit that Doug Cooke took up and provided to the agency. We're now going to the next step, which is starting to look at some of the specific mission areas, the first one here being NEO. And again, we're once again looking for your help and your input to help us shape what should be some of the mission profiles and objectives we do for our robotic missions, what should be the long-term capabilities objectives for human exploration, and what are the technologies that we need to invest in to get us to those end goals. So with that, we have a plan, and we're pressing forward. We're refining it as we get new knowledge, and we look forward to you all's inputs in helping us as we shape this and go forward. Thank you.
Pretty exciting stuff. I really liked what Tom had to say about opening up the third planetary surface. That was exceedingly inspirational. There we go. So precursors. Now that we're opening up to this third planetary surface, we need precursors. We need precursors in order to prepare for human beings to arrive at these new destinations. We did this back in Apollo, and it enabled a very successful campaign there. We started doing it again when we were heading back to the moon with LRO and LCROSS, returning fantastic data in support of exploration and with significant collateral benefit to science. And now we've got a broader, more diverse, very exciting precursor program up ahead, in which we'll be investigating NEOs, still looking at the moon for lunar resources, and precursing for Mars missions. So, a lot of this you've seen already at the exploration workshop, and as Mike had indicated, we've made some changes in response to the RFIs, in response to internal discussions, in response to learning more, and also learning that we didn't know as much as we thought that we did in some areas. And so in some areas, the trade space has opened up. But what we are calling for is a steady stream of exploration robotic precursor missions. And we have that overall architecture as XPRM, the overall missions, and we broke that up into two programs that Mike has indicated. We have XPRP, which are the larger programs. These are going to be more comprehensive in the order of $500 to $800 million apiece. And then the X-Scouts, very exciting, very small, risk-tolerant missions on the order of $100 to $200 million, including the cost of launch vehicle. So very exciting, challenging things. And those X-Scouts are going to be very highly competitive, and that's going to be a wonderful opportunity to get a lot of good ideas coming in from you folks as to how to execute those missions. So why XPRM? Human spaceflight. We're enabling human spaceflight in a proactive sense. We're taking a look at what human spaceflight needs in terms of safety, sustainability, capability, and planning. Precursor missions are going to provide the necessary knowledge to fill the gaps in order to enable those aspects of human spaceflight. We're going to be going out identifying hazards in order to make sure that the astronauts are safe. We're going to take a look at resource characterization and engineering boundary conditions in order to enable sustainability. In order to develop the capabilities to send human beings to these wonderful destinations, we're going to have to understand also those engineering boundary conditions again, and we're going to have to provide a platform for technology infusion to start demonstrating some of these technologies ahead of the use by human beings. And of course, for planning, we got to know where we're going. And so we also have to, as part of the precursor missions, identification of destination selection criterion. There we go. So XPRM complements SMD. A lot of folks are saying, well, we've already got robotic missions going to NEOs. SMD is doing that, and that's absolutely true. However, what we're looking at are the differences in what is motivating us. XPRM, we're looking for missions that are driven by human spaceflight objectives. And it's not that the robotic missions are completing the human spaceflight objectives. They are there to do what's necessary in order for a human being to do their objectives. Now, in the course of doing that, there's a wonderful opportunity for collateral benefit. And you can see that the intersection there, and that's clearly just a cartoon. The size of that little sliver there called collateral benefit is potentially enormous. On LRO and L-Cross, it proved to be very much enormous. And we're hoping to leverage those opportunities to work together for the mutual benefit of the overall industry and the overall field of NEOs. So the top-level objectives and principles, and this chart has not changed one iota since you saw it in Houston. The first and foremost objective of the robotic precursor missions is to conduct the precursor measurements and experiments in support of human exploration. Now, what do we mean by that? We've already kind of touched on that, those engineering boundary conditions. What does that mean? That means gaining the knowledge that's necessary for us to figure out how to grapple with a NEO, how to deal with the environment around the NEO. Identifying the hazards. Is there dust in orbit around here that's going to pose a hazard, or is it a binary system that's going to pose a hazard? Identifying resources. Is there the potential for commercial exploitation of NEOs? Potentially there is, perhaps, but what we need to know is what are the resources that are out there and how can they be characterized and what would be the methods of getting to them. And then, of course, providing that strategic knowledge to inform the selection. We've had a lot of conversation here about what we don't know. Even among the NEOs that we do know of, that Lindley had indicated, and it winnows down to a smaller list, we still don't know the spin rates that might not be acceptable to send a human being to. We don't know if there's going to be particulate in the environment. And so the precursor missions are going to have to fill in those knowledge gaps in order to help inform the selection. Potentially a telescope mission in order to open up the field to other options that have trajectories that are more amenable than the ones that we already have available to us. And also to provide a technology flight demonstration platform. We've got a lot of work going on in ETDD or ETDP, developing technologies. Flagships is one venue, but they're talking about larger missions, demonstrating things on a larger system level. Since we're going, it's a wonderful opportunity to not only demonstrate but infuse some advanced technologies in order to enable these missions. And of course, we operate under several principles of coordination to foster competition, to provide opportunities for instrument competitions through AOs, competitions in our research and analysis activities, competitions in the X-Scouts, a lot of opportunities for all of you to participate. International collaboration. We're actively engaging with international collaboration folks. Kathy Larini is doing a fantastic job of engaging those folks and identifying interest that we might be able to incorporate on precursor missions. And then, of course, to foster participatory exploration opportunities. The stuff we're doing is very, very exciting. Unlike a lot of the SMD missions, and the SMD missions are very much exciting. I've got a long part of my career working for SMD, including on NEAR, as a matter of fact. But the thing that's different is that we're going to where human beings are going to be going. You know, it's a your face here kind of situation. We're going to send a human being here, and that's innately exciting. and a wonderful opportunity for participatory exploration activities. So a little bit on the XPREP program. This hasn't changed a whole heck of a lot. Flight missions, I'll talk about that a little bit later. Clearly they're precursors, and I've already talked about the top-level objectives. We also intend on funding an instrument development line. This is exploration-based instruments to make exploration precursor-type investigations, but to be flown on anything but our spacecraft. This way we can collaborate with SMD, we can collaborate with academia, we can collaborate with international participation and get more data for the community into a broader portfolio of information, and particularly with the diversity of NEOs. I think that the instrument development, because there's so many potential targets, we want to be able to get out to so many of these targets that being able to fund instruments to go on other vehicles can, I think, really enhance our portfolio tremendously. Research and analysis for exploration. We're going to be doing engineering. We're looking at either recasting or resetting up NLSI, the NASA Lunar Science Institute, in order to expand its scope to include NEOs and other destinations for exploration. Holding workshops, issuing grants for research investigations to provide the fundamental knowledge to help plan the missions, and then take the raw data that comes out of the missions and turn that into useful knowledge as well. The X-Scout program, a little bit different. It's smaller in scope, it's very narrow and focused. It's been described by many folks as being a skunkworks aspect. Very small, principal investigator-led. We are also looking at doing some center-led approaches in order to reduce cost. A lot of this will leverage off of the successes that we had with the L-Cross mission, which discovered water on the moon for $79 million. Not too bad. So what we're looking at here is budgeting $100 to $200 million per mission, including the cost of launch vehicle, and trying to, obviously we're going to be making use of a lot of co-manifesting opportunities as appropriate. First launch in 2014, we would anticipate it to be co-manifested with the first XPREP launch. However, if we can get one off in 2013 and find an opportunity to co-manifest elsewhere or come up with an inexpensive launch vehicle ahead of that, let's go for it. Let's try to make this fast. We'll make it aggressive, and we'll try to feed the pipeline of data very quickly. It'll have an 18 to 24-month launch cadence, and obviously, in order to do this as quickly and as inexpensively, we're going to have to be risk tolerant. We'll have a Class D risk posture, the same as we had for L-Cross. So what kind of things are you going to do so inexpensively? Well, we're looking at those threshold measurements, those really key questions in the architecture where you decide if there is this material at this asteroid, we'll go this way, but if there's not, we'll go that way. Key question, threshold measurement, informing very larger architectural branches. That's ideally suited for X-Scout missions. Excuse me. And the X-Scouts in general will be AO competed. And the AOs will be written in accordance with what we're doing in terms of XPREP, and so that we have complementary data sets. And of course, those AOs will also reflect exactly what the objectives are, and as we're doing the architecture development. And so they'll be coming out as a steady stream of AOs and a very fast turnaround in order to answer the questions in a timely manner. So the point of departure for the XPREP portfolio. To handle at the very bottom here, we have the X-Scouts. We're anticipating that first Scout mission to be a NEO. Beyond that, the AOs will be written in accordance with what is appropriate at the time in order to complement the rest of the portfolio and what the human spaceflight needs are. It could potentially be a lunar comm that would complement the lunar lander, potentially. Or could be another NEO mission. On XPREP, that is the wrong chart. No matter. Calendar year. There we go. We saved that one in the chart that you saw with Mike. The fiscal years have a gap between 2014 and 2016 between the NEO and the lunar lander. That's because the lunar lander is occurring late in 15, and then we also have a separation of the NEO and Mars mission. So calendar year actually makes it look a little bit better. It's more evenly spaced across there. So we start out with the 2014 NEO mission, then going into a 2015 lunar lander mission, which basically will provide the ground truth for LRO and LCROSS, identification of resources, some wonderful opportunities for immersive participatory exploration there. Following up with another NEO mission in 2017, and then Mars vicinity in 2018. Now there's some changes here relative to what we showed in Houston. We dropped the Mars 2016 opportunity, and that was a budgetary constraint in what it is that we're attempting to accomplish across the overall portfolio. And we've softened up what our objectives are on Mars. What we really have done also is really started investigating this NEO focus. And so for that reason, I actually have less specificity now than I did in Houston. Because as we started investigating what it is that we need to know at the NEOs, all of a sudden it became very clearly obvious that the problem is exceedingly large. And that's why we really, really need the input of this community. We really need the input of this community in order to help inform the objectives for these precursor missions. Now, your primary objective for today is human mission objectives. But in the breakout sessions tomorrow, we're going to be asking, now that we know what the human objectives are, or at least we have your ideas on the plate, now how do you precurse for that? How do you prepare for that? And those are the objectives that then I would be folding in with the XPRIM team to develop that NEO portfolio. So I really want to focus on the NEO campaign. Okay, so right now we're looking at notionally the 2014 and 2017, and those are calendar years. And we've got this allocation that's basically pretty much a budget wedge on the order of $640 to $840 million, and we're trying to keep them less expensive. We're really trying to be, I can't say better, faster, cheaper, but NEAR was, and NEAR worked. If we're looking at a human being mission in 2025, we're looking at really having the opportunity to only afford 2 of the XPrep class missions. Now, we'll be able to augment with the X-Scouts, okay, but I'm just looking at that XPrep funding portfolio. That's why we're looking at the 2014 and 2017 timeframe. That's going to be monetarily driven, budgetarily driven. So we're really going to have to understand, okay, given that we've only got 2 shots at this, in preparation for a human being mission in 2025, what are the best 2 missions? So we started looking at some various options. We've got the notional shotgunner survey approach in which we go to 3 or 4 or 5 or 6 targets in one single mission. Now, within the range of what we can afford, we're thinking probably, okay, 3 or 4 missions, or 3 or 4 spacecraft going to different targets. But then that's also potentially going to limit the amount of payload that you can take along with you. And then there's some other complications involved with that. Well, maybe let's back down. Let's do a small discovery class, a stack of 2. Maybe send those off to 2 separate targets, and maybe from those targets on to others. So maybe 2 spacecraft go into 4 targets. What about a single discovery class spacecraft? What if we do something that's a larger, more comprehensive measurement, something on a full-blown discovery class, and really getting a good characterization, and then hopefully characterizing multiple targets on the basis of one very in-depth characterization? Maybe that's an option. I'm not saying that any of these are the right answer. And then, of course, we also have the NEO telescope survey, which you've heard a couple of presentations that are indicating this would be something that's inside of Earth's orbit. And then it started identifying additional targets and start getting some very top-level characterizations, perhaps size, spin, albedo, et cetera. So all of these options definitely have potential collateral benefit to planetary defense and potential benefit to science, or collateral benefit to science. But again, the objectives have got to be driven by preparation for human spaceflight. I mean, it's a great idea to be identifying asteroids to count them, what they're there, but what we're really interested in from a human spaceflight standpoint is what are we going to send human beings to, and how do we get the targets that we need for that? So I wanted to make a few words on the NEO telescope survey, and as it turns out, this chart is almost identical to the one that Lindley presented just a little bit ago, so I don't really have to get into it, but suffice it to say that when we started this activity, we were saying, oh yeah, we've got about 40-odd targets we can go to. Yeah, we really don't need a telescope. But then we start applying various filters, in terms of size, of mission duration, of launch window. And you start winnowing down. And in a 2025 timeframe, using this particular set of filters, you got one opportunity. And if you miss that opportunity because a rainy day, launch vehicle's not ready, something else, your next opportunity is in 2036. Well, that's assuming this set of filters. Is this set of filters the right set of filters? Is 180 days really the maximum mission duration? Is the size really the right size? What's the sensitivity of these filters? We have to investigate both sides of this. We have to take a look at what are the right filters in terms of sending human beings to NEOs. What are the real human constraints to this? And then what are the available targets on the other end? And then that'll help inform whether or not this NEO telescope is a good idea for human spaceflight. Rendezvous mission objectives. All the other three classes basically involve rendezvous. And so I kind of lumped them all together here. So what would you be doing? Well, to date, there are a lot of papers out there with a lot of folks indicating various ideas that they would like to do at NEOs. They're all over the map, ranging from flag planting to footprints to mining to towing platinum asteroids back to Earth and cornering the market. Many, many options, okay? When we started looking at this, we started trying to take a look at, well, where have we got this group of people together and started doing things, in coordination with NASA and saying, okay, these are what the community as the community whole wants to do. We really haven't done that yet, and that's why we're doing this here today. But in the meantime, we had to start making some assumptions in terms of the types of things that we'd be looking at. And so we really focused at, irrespective of what the final human objective is, we know that there are some things that are going to be a constant across the board. At least this is what we were assuming. We were figuring that proximity operations, hazards identification, things of that nature, some of the engineering boundary conditions, just of the basic manipulation, irrespective of what the objective of that manipulation is, these are the types of things that we would probably be looking at for the robotic precursors. But we're looking at you to help us inform that. Are these the right set of assumptions? What else are we missing? What human objectives are we actually looking for? And then, once we know what the human objectives are, what are the knowledge gaps that we need to fill before we send those human beings? And that's really what we're talking about here in terms of these precursor measurements. So the near-term planning activities, starting out over here, we've got the ExploreNOW, which we're at right now. John had mentioned earlier that we also plan on having some technical exchange meetings among the NASA NEO community in order to start winnowing down some of these mission types, using those inputs, using the inputs from here today in order to get that, to start winnowing down those mission types for that 1-2 punch in preparation for 2025. And then we start getting into mission definitions. And here's where the public gets involved again, where we plan to establish some objectives definition teams. This is modeled after what the science mission director does in terms of science definition teams in preparation for missions. This is to identify the specific mission objectives, the types of measurements that would meet those types of objectives, and then strawman instrument payloads that could meet those measurement objectives, to meet those measurements to make those observations. I got that a little mixed up, but I think you followed me. And of course, we'll also be doing some mission concept studies in order to help support that effort. So that will get us to a mission definition, candidate mission definitions, from which we could then hold a functional acquisition strategy meeting. That's an internal meeting, which we decide how we're going to go about doing our make-buy decisions. And then we start issuing some, getting ready for procurements as soon as we get some authorization on this program so that we can start buying some payloads. So the important thing, though, is that we're getting your input here at the ExploreNOW. We're getting your input again in the objectives definition teams, and this will not be the last workshop. So in summary, we're uniquely poised. This is a wonderful opportunity if we're going to have human beings going to the third planetary surface in 2025. The precursor missions are here to support that. This program is aligned to those objectives explicitly. No other program actually is directed toward the human spaceflight objectives. And so far, we're consistent with what we know. But we're also pretty clear that we know what we don't know. And we know that we don't know a lot. And that's why you're here, is to help us fill in those gaps. So in terms of filling in those gaps, I just wanted to give a little bit of a prequel of tomorrow. Today, when you get into your breakout sessions, you're going to be discussing the human objectives at NEOs. Marguerite will be talking about that in a little bit later. I wanted to point out that that is human objectives, human mission objectives. That then feeds into what do we need to know in order to do the human objectives. That's where the precursor requirements come from. is filling in the knowledge gaps for the human objectives. These are not human objectives. This meeting is about the human objectives. But we're going to get in then to the knowledge gaps to prepare for that, the precursor measurements that would be associated with that, what type of measurement is that, indicate for the categories that I talked about before, and how critical is it to fill that knowledge gap in order to enable the human objective. Then, if we do a good job on that, bonus question, and this is the fun one. So I encourage you all to really think about this one so that you can have a lot of fun with this one. Given that you only had one, given the fact that you're going to have a NEO mission of your choice in 2025, what 2 precursors would you send? Mission number 1, mission number 2, and why? Very open, a lot of fun with this question. That's why it's a bonus. So we get good input here. We can discuss this tomorrow. And of course, I'll be gladly accepting any inputs on 3x5 cards or however you want to give them to me with respect to these mission ideas, as well as you're going to talk about the fact that we're accepting input on the web as well. And if you have any questions or comments and you want to talk to me, you'll see me around the hall. Thank you.
Well, first off, a big thank you to all of our speakers. I think this has been excellent, both on time and on target for the content. I think what we've gotten is a great start, a solid base plane. I think we have a strong agenda for the rest of the day, and it will be interactive, particularly towards the end of today and certainly all of tomorrow. With that, I would like to give you a public announcement in that all of these briefings are posted on the website. And so this is all about communication and ready access to it. And so I encourage you to reference and share since this is all about bringing the community together. As we return, we're going to take a break right now we will return and start promptly at 10:15. However, I would like to give you just a reminder. Pardon? We're doing a 15-minute versus 30. We'll stick with what I said. 10:15. We'll return, and but my conscience is back there.